Alright, today we are going to study some of concrete, discrete probability distributions. But before that, I will introduce the notion of probability generating function. Okay. This is similar to the moment generating function, but this one not like unlike the moment generating function. This is only applicable to discrete random variables that take non-negative integer values. Okay, let's say k is a random variable that can take values 0, 1, 2, and so on. So the probability generating function, or simply PGF, is defined as this, which is the expectation value of power of s. Uh, Sorry, this k should be uppercase. So this s is a variable here, but it doesn't have any meaning. It's just introduced for convenience. And this, according to the definition of the expectation value for a discrete random variable, in this case it will be the summation from 0 to infinity s to the power of k and probability of k. Okay, so compare this with moment generating function. So we can also define a moment generating function for this random variable like this: expectation value of exponential of tk. Okay, so just this difference. So this can be, moment generating function can be defined for any random variables, now, which can take negative values or non-integer values or whatsoever. But this probability generating function can be defined for only for random variables that can take non-negative integer values. Okay, so let's study some properties of probability generating function. First, if you put s equal to 1, then you will get expectation value of, okay, this is 1, which is just 1. So it's not very interesting. Now let's differentiate this function once with respect to s. So that is this. So if you look at this definition, the only place where you have s is this. Okay, so yeah, just try differentiating the definition. Okay, it should be large K, and actually, since we can swap the order of expectation and differentiation, so we have K S K minus 1. Okay, now if we put s equal to 1, then we have expectation value of k, right? Just s equal to 1, and this part is just 1, so it's expectation value of k. Then let's differentiate the first derivative of probability generating function again. So in this case, we have this. In this case, now if you differentiate this, you have expectation value of k s k minus 1 ds, and you have expectation value of k minus 1 s to the power of k minus 2. Again, if you put s equal to 1, then you have this part 1, so k minus 1. So distribute this k, expand the expression. We have k squared minus expectation value of k. So if you combine this with the previous result, where we got expectation value of k in terms of the first derivative of the PGF, then you have expectation value of k squared. So add this and this. G2 prime plus G prime. Okay. And again, combining with this and combining this and this, you can have an expression for the variance of k. So that is the use of probability generating function, just like the moment generating function. So expression for the variance of k, if you use this formula, expectation value of k squared minus square of expectation of k, then the first part is this one. So G2 prime 1 plus GK, and the second part is just square this one, so minus G prime K of 1 squared. Okay. And let's see another important result for probability generating function. So let's say x and y are independent random variables. Random variables that take non-integer values. Okay. Then let's define a new random variable z by x plus y. Okay. And if we have the probability generating function for x and the probability generating function for y, then what is the probability generating function for z? Sorry. The result is this moment generating function can be expressed as the product of to probability generating functions. So this is also just like the moment generating function. Okay. So proving this is an exercise, but I will give you a hint. So in the definition of the moment generating probability generating function, we have something like this, right? So in this case, the power, it will be power of z. Okay, but by definition, it is x plus y. Okay, and we have x s to the power of x times s to the power of y. Okay, so this is already looking like product of these things. So we are assuming x and y are independent. So the joint probability distribution of x and y can be decomposed into a product of two distribution for x and y. So just calculate that and you can show this result. Okay. Now we study some concrete distribution for some random variables. The first one is the easiest one, called Bernoulli distribution. So this is not Lee, it's Yi. I think it's a French name. Bernoulli was I think he was Swiss. Yeah, so it's not Bernoulli, it's Bernoulli distribution. Okay. This distribution is defined by this random variable. It's a distribution of this random variable. X is a random variable. This is either 1, 0 or 1. Okay. And the probability that x is equal to 0, x equal to 1 is given by p, where p is between 0 and 1. Okay, and probability of x having the value of 0 is q, where q is 1 minus p. So if you add this and this, it adds up to 1. Okay. So this is called Bernoulli distribution with parameter p. So this p is this p. Okay. For example, let's calculate the probability generating function of the Bernoulli random variable x. Okay. So by definition, it is the expectation value of s to the power of x. Okay. But x can take only 0 or 1. So when x is 0, s to the power of 0, and the probability is q. When x is 1, the probability is p. But s to the power of 0 is 1, so we have q plus ps. So this is the probability generating function of x, of a Bernoulli random variable. Okay, so if we differentiate this function with respect to s once, we get p, right? Just differentiate this, we get just p. So, and this is already a constant, but anyway, if we substitute s with 1, it's still p. So that should be the expectation value of this random variable. Okay, and let's check this using the original definition for the expectation value. Okay, original definition was this. In this case, x can take 0 or 1. So x, probability that x takes value of x. So 0 times probability of 0. 1 times probability of 1. So this is 0, and so yeah, this is 1 times p, so that's p. Yeah, so same. So this is correct. So this is p, this is p. Okay. What about the variance? Okay, so variance, in order to get variance, first we differentiate the probability generating function once again, but the first derivative was already a constant, so the second derivative is 0. So the variance of x is second derivative, first derivative minus square of the first derivative, right? This is 0. This was p. This is p squared. So what we have is p times 1 minus p. And 1 minus p was defined as q, so let's use this notation. So that's pq. So this should be the variance. Okay. You can check if this is correct by using the original definition of the variance. Okay. That's very simple.